Ooh. All right. We're gonna get started. I'm gonna have us start with this question of how do you know whether this is salt water or fresh water? Can you tell just by looking? What do you think? How would you know? How would you know if this is salt water or fresh water? What are some of the tests you could do to determine? How would you know? So, one of the ways that we're going to approach today is we're going to take what we learned from last week about salinity and salt water, and we're going to use that to help contextualize what we know about freshwater. So take a moment and some more notes. Think about the test you do if you were given water and what you would use as evidence to determine whether that was ocean water or freshwater. So let's say you're working at Monterey Bay Analytical Services. It's a blind test, so you don't know where the source is from. It could be the Atlantic Ocean, it could be the Pacific Ocean, could be Lake Tahoe, but you're given a water sample. How would you know whether that sample comes from the ocean or from freshwater? So take a moment and somewhere in your notes, give at least two examples of how you would know. What are some tests you could do that would help you determine whether or not that sample was freshwater or saltwater? So I'd love to hear from you. What are your thoughts? What are some examples of how you could determine if a sample that you didn't know its location was saltwater or freshwater?
I would probably try floating something that I know typically sinks in fresh water but would float in salt water since salt water has a higher density.
Awesome. Density is a great test to do. That's an excellent way to determine saltwater or freshwater. What's another example of a test we could do? We might be able to measure the concentration, so we could look at absorption, right? Choose something that um, we can know the concentration of as a reference standard, and then using Beer's law, we can determine absorption. Now, granted, that would have to be different between saltwater and freshwater, but that's another example. Um, a great one, right, could be we could essentially remove all of the water, right, by evaporation, and then look at the salt components that remain. So there are lots of ways we could be able to determine this. So our focus today is we're going to move from the space where we were thinking about briny water and saline water, and we're going to move into brackish water and fresh water. Really interesting. There are some cool spaces. So the Elkhorn Slough is a good example. Um, but there are other estuaries in Florida. There are mangrove swamps um, where there's essentially this mixture of ocean water and fresh water that's called a halocline. We'll be looking at that today. And then we'll think about lakes themselves or rivers. What are fresh water? So, in order to do that, we're going to do a couple of things. So, last week we talked about the ions most present in seawater, so chloride and sodium. And we talked about how to calculate concentration in parts per thousand. So, if we think about our predominant ions, right, we've got the amount of chloride, the amount of sodium, but there might be other things that are osmoles, like sulfate or magnesium or calcium or potassium. And we looked at bicarbonate to talk about buffers. So we'll come back to that today with a couple of examples. So, interestingly enough, salt water, which is found in the Earth's oceans and seas, is the predominant amount of water that is here on Earth. Fresh water that's contained within lakes, rivers, and streams is actually present in a much smaller amount. And then a halocline is what results when fresh water from a river or a stream drains into a saltwater body and lowers the saltwater salinity. So I want you to take a moment and sketch in your notes. You're going to do two things. So let's assume that we have our Pacific Ocean to the west, And we have our beautiful California coastline. So we're going to think for a minute, what happens when, say, for example, the Salinas River comes into the ocean? What are some of the things that you think might occur? So we've got our mental model, we have our Pacific Ocean, we have the Salinas River, and we're really interested in thinking about what's happening in this space. So what are some of the things that you think might be occurring in this space? So in our Salinas River, what are some of the things we might have? Well, we could have silt or runoff. The Salinas River supplies water for many of the agricultural fields in the area. So that runoff could include fertilizer. It could include nitrates, nitrites. It could include pesticides, right? There's a lot that could be present in the water of the Salinas River. And those are chemical as well as organic or living biotic organisms. And then if we think about our Pacific Ocean, right, we've just spent time last week thinking about the ions that are present. So our chloride, our sodium, our bicarbonate, as well as other ions. So what happens when those mix? Well, there's a couple of things that, right, are worth considering. So organisms that live in the Pacific Ocean, say for example our algae, are fed, right, by upwelling that occurs in the ocean. When we have a mixing of the Salinas River that's freshwater with the Pacific Ocean and there's discharge, right, there's a change in the concentration in that space. So the nutrients might look very different. So part of what we're going to be thinking about with this mental model are some case studies. And we're going to think about, well, in each of those cases, how do the concentrations change? What might make an impact, say, for example, on areas where water is mixing? Okay, so hopefully somewhere in your notes, you have an example of this mental model. We're going to come back to this model with a couple of the problems we're going to think about today. Okay, so the other thing that we talked about at length last week was using parts per million. But it's important here to say that there's also, in addition to parts per thousand and parts per million, there's parts per billion and parts per trillion. It's super unfortunate that PPT can mean either parts per trillion or parts per thousand. Today, the convention is typically that PPT is parts per trillion. Um, Interestingly enough, when folks want to use the parts per thousand, they often refer to that as per meal or the 0/00, um, the fractional. And the reason why we're going to make sure that we revisit these is because of a couple of key examples. So parts per million, for example, we could refer to the mole fraction, the amount of carbon dioxide that's in our atmosphere. We could think about parts per billion in terms of the amount of ozone uh, that is adequate and appropriate for our air quality. You could think about, say, for example, NO or nitrogen oxide, um, and the amount of NO that's present in the air we breathe normally. And so the reason why we're going to use these values is because we want to be able to think about, right, when is it appropriate to use parts per million versus when is it appropriate to use parts per billion. Um, and we're going to see some examples, and this is actually, I think, important where the chemical is so detrimental, say, for example, to humans or to other organisms, that it can be present in a very small amount but cause incredible damage. And that's where it would be appropriate for us to use parts per trillion. So at this point, hopefully you got practice with your pattern of inquiry doing calculations. So converting between parts per million and milligram per liter, or parts per billion and microgram per liter, or parts per trillion and nanogram per liter. And so what I want us to be able to think about today is the relationship between those and how you interconvert. So a good exercise for you to practice that we're going to see on our next pattern of inquiry, right, is being able to look at, say, for example, contaminants and the amount of part per million, part per billion, part per trillion, and interconvert between those. So hopefully you feel comfortable with that. We're going to do one example together now, and then you'll have the opportunity to practice more. So let's say, for example, that we're thinking about the amount of lead in water. Does anyone remember from the article that we read how much lead is safe, right? So what's the threshold from the EPA for the amount of lead that's okay to have in water?
15 parts per billion.
Yeah, you got it. Okay, so um, we've got 15 ppb. Ooh, it erases. That's kind of cool. Sorry, I've been trying out new pens. All right. So if I wanted to know how much lead that was, right, in micrograms per liter, well, I would know that 1 ppb is equivalent to 1 microgram. So I could easily do that interconversion. But if I wanted, say, for example, to know, well, how much is that in parts per million, right? Because maybe I'm given a table and the information that I'm given isn't in parts per billion, it's in parts per million. Well, then I could do a conversion. Oh, I need one more P there. So 1,000 ppb is 1 ppm. So being able to interconvert between these values can be useful. And it's oftentimes essential because sometimes we're given information, say, for example, in a table from a textbook or in a report in a primary literature article that's in one value, but we have to interconvert to be able to get to the other value. So it's just a useful skill to have. Hopefully you feel comfortable doing those interconversions. All right, the next piece that we're going to take a look at is going to ask us to build our own table. So in this case, you're going to think about the ratio. So 1 part per how much. You're going to figure out what the percent of that is. And then you're going to show, well, what's the value in ppm? What's the value in ppb? And what's the value in parts per trillion? So this is a really good exercise. I'd like for you to try to do this on your own, and then we're going to check in on Thursday and compare our tables together. So this is a really good thought exercise. Give at least 3 to 5 examples so you feel comfortable doing the calculations. It doesn't have to be exhaustive, but it should be enough to kind of show you the interconversion between the values. So that's a task for you to do today or tomorrow, and then we'll come back and check on that on Thursday. Okay, we're going to talk today about freshwater. So we know that freshwater is a low concentration of salts and other dissolved solids. And we know that saltwater is found in the oceans and the seas. So our big idea here is that freshwater is less than 0.05%. Um, so if we think about the amount of ions that are present and we do a calculation, less than 0.05% means that, oops, sorry, went too far. Means, all right, 0.05%. Well, let's think about that. How do I get 0.05%? It means that I have 5, right? 5% out of 100 would be 5 grams of salt and 100 grams of my water. 0.05 means I have 5 grams in 10,000 grams of water. And, right, it's important here to note that this is the total amount of salt. Interestingly, we're going to spend a minute and think about brackish water. So this is, right, between 0.05 and 3%. So if we think about the comparison, right, brackish water, choose a different color, is our 3 grams per 100 grams of water, and that's our 3%. So if you want, right, to know whether or not something is pure fresh water, or if it's brackish or could be considered a halocline, then you would be looking, right, for concentrations that are in these ranges. Now, you can obviously do the interconversion to get to moles or parts per million, parts per billion, parts per trillion. But one of the things that we're going to do is we're going to look at some data about water and make decisions. Well, is it fresh water? Is it brackish water? And interestingly enough, there are very specific regulations on fresh water that you can drink, largely because of safety purposes. So I'm super excited for the case studies we're going to take a look at today. Before we can do that, though, it's really important. So Jackie mentioned density. So we could use density as a test of our fresh water. And we know that saltwater is denser than fresh water. So it's also going to be something that is temperature dependent. So warmer salt water is less dense than colder salt water. So the colder salt water is going to sink to the ocean floor. So when we think about the water column, colder water is denser, right? When ice, say for example, freezes, so like if you were to go up to where there are glaciers, right, the ice freezing, it becomes less dense and it floats on the surface. So there are differences in the density, really, and differences in the amount of salt within the water column itself. So this ties back to what we were talking about in the very first class where we looked at colligative properties. So both the freezing and boiling points of ocean water are going to differ from fresh water. So this is another example of a test that you could do. But really, in nature, only the freezing point is of concern. So the average freezing point for ocean water is -2 degrees Celsius. Although, right, if it's under pressure, so if the salt content is higher or if you're deeper in the ocean, um, then it can have a slightly different value. Whereas the typical freezing point for freshwater is 0 degrees Celsius. So you could also measure how quickly or easily that water freezes. Another way that you can tell the difference is the tonicity. So when water that has different concentrations of salt, or really any solute for that matter, is positioned across a semi-permeable membrane, water is going to flow to the side of the membrane that has the higher solute concentration. So, for example, if you had multiple samples and you needed to determine which were ocean, which were freshwater, you could look at movement across a membrane, and that's particularly important for the plant and animal species that live in a body of water. For example, there are some species of amphibians that really thrive in a halocline environment. They're better in brackish water than they would be in the ocean or in freshwater. Likewise, there are some species of fish that can only live in freshwater, right? Whereas there are other species of fish that are capable of moving from ocean water to a halocline environment. Uh, and then the piece that probably is really interesting for us to think about is this osmoregulation. So we talked about tonicity, right? And how the reason saltwater is something that you don't want to be in for a long period of time is because the water that's in you will leave your cells, right? And you'll essentially contribute that water to the salt water because its concentration of salt is much higher. So this means that organisms lose water to their environment, so they have to constantly drink water and eliminate salt. So on the other hand, fresh water is actually hypotonic to some animals and plants. These organisms rarely need to take water, but they often have to excrete it um, because it's absorbed readily as an effort to kind of even out the salt concentration. So this adaptation, and that occurs for all living organisms, is known as osmoregulation. So it's really this question of how does that organism in its environment, is it absorbing water or is it releasing water based on the tonicity? So this is the super cool part about the aqueous chemistry that we're going to get a chance to think about. So total dissolved solids is measured in parts per million. So fresh water isn't just water. There's often many other solutes that could be dissolved in the water. And so you've probably heard people refer to soft water or hard water when it comes to, say, for example, washing clothes. Or we often think about total dissolved solids in the way that we purify water to make it safe to drink. And then if you're doing research, sometimes it's really important to have water that has all of the ions removed. We refer to that as deionized water, but it's been critical in order to conduct certain types of experiments to be able to remove, say, for example, ions or other minerals. So we're going to take a minute and just unpack this a little bit. So soft water, what does that mean? If you look at this figure, how many total dissolved solids are in soft water?
Like 0 to 50. It's like less dissolved solids.
Yeah, right. So there's, yes, yep, there's a lot less solids in soft water than there is in hard water. Now, I don't know if you've been, say, for example, to the grocery store. Sometimes folks will sell mineral water, and that water has actually minerals that have been added to it. And you'll notice, right, that mineral water that is bottled can have upwards of 400, sometimes even 500 um, parts per million of total dissolved solids. Interestingly, the EPA has a maximum contamination level that says, hey, look, you have to have, right, less than 1,000, right? Or sorry, greater than 1,000. Misread that. Greater than 1,000 in order to be considered salt water. Everything else below that, we're going to consider fresh water, but with, right, a variation in the total dissolved solids. So let's think about then how we purify our water. So tap water has this really interesting range that is different regionally. In fact, we're going to see some examples of that. But tap water can be anywhere from 150 all the way up to about 400 parts per million in terms of total dissolved solids. This is where, say, for example, if you use tap water and you use a Brita filter, right, that filter can remove some of the total dissolved solids and that way lower the amount in ppm. If you wanted to purify water, say, for example, sometimes you'll see folks label it as a mountain spring water, and usually that's because the water is filtering through either natural carbon or, in the case of many of the companies that bottle water, a carbon filter that's been applied. And then there are other ways to remove even more of the total dissolved solids, and that's reverse osmosis. So that's using a membrane, essentially, where you separate out the total dissolved solids from the water. And sometimes you can also do that in combination with distillation, where your pot keeps all of the ions, and essentially what comes over as the distillate is just the water. So there are several different ways that you can purify water in order to change the amount of ions and specifically total dissolved solids that are present in parts per million. I chose this because I think sometimes conceptually it's tricky for my brain to wrangle what parts per million really means. So the example here, the bottle on the right contains 1 million beads, but only one red bead. So that's an example of 1 part per million. The other colored beads, so in the bottle that's on the left-hand side, represent 10 ppm, 100 ppm, and 1,000 ppm. So you have red, right? You have yellow, and those are present in different amounts. So I think the visual sometimes is really helpful. Okay, I want you to take a moment and somewhere in your notes, I want you to sketch a cube. This is my best attempt at a cube. It's not perfect. Your cube doesn't have to be perfect, but sketch a cube. We're going to use this cube to help us make sense of these dimensionless quantities. So 1 part per million, right? So the value of 10 to the 6th, I should add here. Sorry, I'm missing my hat. 10 to the 6th. Total parts, 1 part per million would be 0.050 and a 1. We talked about the parts per thousand or the percent meal. And again, this would be 10 to the 5th, the value of 1 part per thousand. Ooh, so this shouldn't be 10 to the negative 5. What should that number be? Right? If it's per 100,000, right? So that's just one more. So here, right, 0.00. So instead of 5 zeros, it's 4 zeros and a 1. And this is going to help us as we build out that table, right? 10 to the 4, 3 zeros, and a 1. And then parts per thousand, this is the per meal. Notice the difference here is percent meal, whereas here is per meal. So that's going to be 0.0001. And then 1 part per 100 is usually represented by the percent sign, but you can think of it as 0.01. So this is the first column in the table that you're building. So you can have labeled the quantities, and then you know how much the ratio is, or the part per, as a result of participating or constructing this table. Okay. I promised that we would do buffer calculations. So we're going to do 2 together, and then you'll have the opportunity to do a couple more. So we're going to start out with our H2CO3. And here we're going to build a buffer, and then we're going to think about what happens to that buffer when we add an acid or a base to it. So when I think about how this ionizes, the first thing it's going to ionize to form is H plus as the aqueous ion. And HCO3 minus. We look at this particular buffer because of ocean acidification and the carbonation of shells, for example. That's why this is relevant. So we have 2 pKa values. The pKa1, the first deprotonation is 6.3. So that's what we're going to use. So let's say we're thinking about ocean water, right? And we're going to use a pH of 8.2. It's the other piece of information that we have to know. And we want to know how much of the conjugate base is present. So that's the question that we're going to be answering. How much of the conjugate base is present? So I'm going to label these. So this is my conjugate base. This is my acid. So in my calculation then, there are a couple of things that I'm going to be doing. The first thing that I'm going to do is my Henderson-Hasselbalch equation. If you took biochemistry, this should be familiar to you. But if not, that's okay. We'll just refresh our recollection. So pH is equal to pKa plus the log of, in this case, I'm going to see if I can use color to help us out. Our conjugate base, so that's A minus, over our HA. So I can plug in what I know. My pKa value goes here. My pH goes here. So 8.2 equal to 6.3 plus the log of A minus over HA, where I don't know what this ratio is. That's what I'm going to be solving for. So the first thing I'm going to do is subtract 6.3 from both sides. Oof. It's kind of like a 3. Okay. Got my calculator. So 8.2 minus 6.3 is 1.9. It's going to be equal to the log of A minus over HA. When we resolve logs, for log base 10, we have to do 10 to the power on both sides. So this becomes 10 to the 1.9. That's going to be what resolves our log. So if we do on your calculator, it may be a shift button. So I get 79.43. So A minus over HA is equal to 79.43. Now, how do I convert that? Well, this, right, is the same as saying 79.43 moles of A minus over 1 mole of HA. So what happens, right, if I add base to this? So that's the first problem we're going to consider. So we've done our first calculation. We know the amount of conjugate base we have. We know the amount of acid that we have, right? And so at equilibrium, right, when H2CO3 is in water, we have 79.43 moles of A minus for every 1 mole of HA. And that's what our pKa is going to tell us. Okay, so we're going to hold that information. For our purposes, we're just going to say it's 79 to 1. So move this. So what we're doing now is actually a really cool application of a buffer. So let's say that we have an ice table. So our initial amount here is going to be whatever, right, our concentration is that we started with in terms of our bicarbonate. But in this case, we're actually really interested in 1 mole, 79 moles. And so for now, we're going to leave this H plus blank. Now, let's say we've got a change. So you could add acid or base. The first example we're going to have, because it's got H plus here, is we're going to add acid. So let's assume that we have 0 of this. But let's say that we're going to add acid to our solution. It could be HCl, anything that is donating H plus. And let's say that we add 1.5 moles. Okay, so if we add 1.5 moles, what's going to happen in our buffer? What's going to react? So that's our change. We've added 1.5. So the 1.5 that we add, right, is going to consume 1.5 of our bicarbonate. And it's going to generate H2CO3. So in our ice table, it's important to know when you're making a change, where you're putting that change. So in this case, right, if you put the change here, it's probably better for you to represent it as, well, in this case, we're going to add 1.5, and we're going to consume 1.5, because then our ice table makes a little bit more sense. But your call, you can shortcut that as you wish. All right, so what does that mean for our equilibrium? Let's think about that. So in this case now, we have 2.5, right? And now we have 78.5. And then because we know the pKa, we can plug that in. So 6.3. And we've got 78.5. And we've got 2.5. So take a moment, do that calculation with me. Let me check, make sure that I'm on the right track. So log of 78.5 divided by 2.5 plus 6.3. So I get a pH of 7.796. Ooh, and we can round that up. So 796, I can round that up to 8. Okay, so if we think about where we started, we had a pH of 8.2, right? And we added acid, and the result was our pH decreased, which makes sense, right? That's what we would expect and or hope to see. Okay, so those are two examples of calculation. So the initial calculation of given a pH and a pKa determine the ratio of conjugate base to acid. And then the second one is, well, what happens when you add, in this case, an acid? How does the pKa respond? Okay, so let's do something similar, but now this time, I want you to think about, well, what happens if you add a base? So we're going to have to rewrite our expression here, because now we've got our acid. And this is a really interesting question, because when you add a base, what is the base going to react with? Does it react with our carbonic acid, or does it react with our bicarbonate? What do you think? The short answer is it's going to react with, right, the carbonic acid first, but if there's strong enough base and or if there's base left over, it can also react with the HCO3. So if I add base, I want to know what's going to happen here. So we're going to use the same thing that we did before, except now we're going to do different color. All right, so we had 1 of our carbonic acid, we had 79 of our bicarbonate, and let's say we add 1.5 of our base. Right, so in this case, right, 1 of this is going to react with our carbonic acid. We're going to completely consume that. And then 0.5 is going to react with our bicarbonate. So we have 0 here. We have 0 here. Ooh, now this gets a little bit messy, right? Because in reality, we know that nothing goes to 0. So the reality is there's going to be a very small amount of our acid that's left over, because, right, even in an equilibrium system, if I pull all of my bicarbonate over, right, and I have no H2CO3, then equilibrium is going to shift to try and achieve that equilibrium. So this is where it's really useful for us to think about, we can do a calculation, right? So if we plug the numbers in, it would be, right, 6.3 plus the log of 78.5 over 0. But if we actually try and do that, all right, then we're going to get an error. So the reality is that 1 is probably the lowest you can go in terms of being able to think about the impact of base on your situation. So in this case, right, let's say that we didn't completely consume our carbonic acid. Let's say we only added 0.5. So we get 0, 0.5, and then this becomes 0.5. This becomes 0.5. Okay. So here now, right, we can still do this calculation. So 6.3 is equal to, oh, sorry. Let's fix that. 6.3 plus the log of 78.5 divided by 0.5. So if we do that calculation, we're going to see so we get 2.19 plus 6.3, so 8.49. So our pH increases, which is what we would expect to see. Okay, so we've done a little bit of practice in terms of buffer calculations. You'll have the opportunity to take a look at some more of these. The most critical pieces for you to keep in mind are the following. Whenever you're doing these types of calculations, you need to be able to identify, right, your conjugate base and your acid. It's also helpful to know, say, for example, that there are complex equilibria at play. So here's a really good example. HCO3 minus still has a hydrogen that can react. And so that's a really important consideration for us. Okay. I'm going to stop sharing for just a moment because I want to show us the opportunity that we're going to do on the Canvas page today. So let me pull that up. In your go. So in Canvas, we've got case studies that we're going to take a look at. So we're going to read through these. You have a choice to sign up. There are 3 to choose from. There's Weedrun, the Salton Sea, and Pajaro. You can sign up for any one. Sign up is here. And on Thursday, when we come together, we're going to share out about your case study. So let's take a look at the case study for Weedrun. So what you'll notice about these is that you're given a context. Ooh, I can make that a little bit bigger so it's easier to read. So you're given some information about a page, and then you've got some questions, right? So what is the problem? What might have caused the problem? How did the problem come to the attention of local residents? What data would you want to assess? And then there's some additional data for you to take a look at for that article. I think that this assignment should take about 20 minutes. So my ask for you is that you choose one of these case studies and prepare it for our time together on Thursday. Are there any questions about this assignment? Okay, let me make sure I publish this so everybody has access. Sweet. Okay. So if you refresh your Canvas page, you should have access to the pattern of inquiry for buffering. So that's going to be due next Monday. Let's take a look at that for a minute, in addition to our case studies. Okay. So I'm going to ask you to do a little bit of refresher recollection around acids and bases. And if you need to look this up, that's totally fine. The OpenStax Chem2E is a great place to find this information, but it's also widely available from multiple sources. We've got some examples of what is a conjugate base, what's a conjugate acid, and being able to identify the components. And then it's useful for you to do some calculation practice. So I've got practice for calculating pH and pOH, and then determining whether something's acidic or basic. And then we've got some equations that are going to help you to calculate the pH, the ratio of the conjugate base. And we're going to have you work with disodium hydrogen phosphate buffer. It's a very common buffer. So I've given you all of the equations that you need to be able to do that calculation. And then for the evaluate, you're going to look at preparing a buffer solution. And that's for acetic acid. And then for the create, you're going to calculate the pH for what happens after you add a base, in this case, sodium hydroxide. So each of these is going to ask you to take information that we learned from last week and what we're learning this week in order to make sense of these problems. It's super exciting because I feel like you're going to see examples in molecular biology of these types of buffer calculations. If you work in a lab, it's very common as well. All right, so last piece for us to take a look at. I know that you all had your reading quiz that's due today. That was the only that was a combination of kind of the two articles. So you could choose either Flint, Michigan, or the article about ocean acidification. And so the first part is you submit your questions. The second part is I'm going to email those questions out to one of your colleagues, and you'll have the chance to answer them. So we'll do that exchange via email. You don't have to submit anything online, but we'll be talking about both of those articles on Thursday as well. So you've got a couple of things you're working on. Don't forget, if you need examples of the buffer calculations, they're here in the deep dive. So please sign up for your case study. We're going to be discussing those on Thursday. If you have questions about the pattern of inquiry for buffers, let me know. Delightful news for you. There's no exam too. But I am going to share some resources from the library for your upcoming community water project, and that's what we'll be talking about on Thursday. So that's all I have for us today. Any questions?